So, good evening, students. Good evening, Khan Deepan and Ganesan Sabarman. Last class, we have seen about some aspects of periodic table. Good evening, Krishnaswamy. So, till some more students had good evening, Madhi, Sagi, and Karthik Gunasegar. So, this with this last class, we have seen about the introductory aspects to periodic table. So let us revise briefly till some more students add to the group. So this one, so period is about we are aware that now about 120 elements have been identified in the earth crust so far. So each we cannot remember each and every element individually with the name, properties, etc. so forth. It will be convenient if they are put in the form of a group or table. So following some pattern, a regular pattern. So that will be convenient. On that, first triads, groups of 3 elements were observed. Then octets or octaves, groups of 8 elements were observed. All these went well up to calcium. So good evening, Padma Krishnan, Santosh Bhavani, and Geeta Kannan, also Kannapan Rajendran. So this triad, concept of triad, which is a group of elements, 3 elements showing similarity in their properties. Octaves is the group of 8 elements showing similarity in their properties. It went well up to the element calcium, whose atomic number is 20. Afterwards, it was erratic. So later on, Mendeleev, who is the pioneer of periodic table. So periodicity is the repetition in the properties of elements at regular intervals in the table. That is called periodic table. So it was first proposed by Mendeleev. So he proposed the law, Mendeleev's periodic law, which states that the properties of elements are periodic functions of their atomic weights. Properties of elements are periodic functions means repetitive functions of their atomic weights. So as the atomic weight increases, periodically the properties would be similar. So he constructed this periodic table called short form of periodic table. This periodic table consists of array of elements, that is arrangement AR or AY. Array or arrangement of elements ordered in rows and columns. The rows were called periods and the columns are called groups. So he constructed a tabular form. So later, Mendeleev and Laudermeyer published nearly identical classification. So this is given in your book. The second sentence is to be noted. What is meant by periodic table? Periodic table is based on the similarity of properties and reactivities exhibited by elements. So later, Henry Moseley modified Mendeleev's periodic law by the property. It is not the function of atomic weight, rather it is the function of atomic number. So Moseley's modern periodic law or Moseley's periodic law is the same law as that of Mendeleev periodic law, except for the last two. Good evening, Dhanalakshmi. So last one word. So Moseley's periodic law says that the properties of elements are periodic functions of their atomic numbers and not the atomic weights, because atomic weights slight variation, some limitations against opposite examples were observed. So elements with higher atomic weights were placed before all these. Good evening, sir. Joel sir. Now this one, array of elements or group of elements and periods, that is the basis for the Moseley's periodic table. Moseley's periodic law states that the properties of elements or periodic functions of their atomic number. Now Important features of Mendeleev's periodic table, last class we have discussed. Let us once again briefly tell. So the horizontal rows of elements, they are called periods. Vertical columns of elements, they are called groups. So up to 7th group, the elements, so maximum 2 elements, either 1 element or 2 elements were there. But afterwards, 8th group, more than 2 elements were observed. So there is a anomaly in their placement, etc. So these are the limitations. But advantages of Mendeleev periodic table, he could predict the properties of the elements which were not discovered during his lifetime. That is germanium, silicon, germanium, gallium, like that. He named them as Eka aluminium, Eka silica, like that. Eka means expected element. So element was not observed during his time, but he could predict the properties. So that is the merit of the periodic table. Good evening, Dhanapa, Alavar and Harshit. Now, the vertical columns of collection of elements, they are called groups or families. Horizontal columns of or rows, horizontal rows of elements, they are called periods. So generally, periodic table consists of 7 periods and 8 groups as per the Mendeleev form. So groups were once again divided into subgroups, subgroup A, subgroup B, except the groups 0th group and 8th group. 0th group only one type of group, 8th group also only one type of group, but other first A, first B, second A, second B, third A, third B, like that. So first to 7th groups were divided into subgroups as A group and B group. So this was the arrangement of Merritt's periodic table. He gave an elaborate classification based on the physical and chemical properties. He predicted the existence of unknown elements, left some gaps, naming them as Eka elements. That is the advantage, merit. So this scandium was not discovered during the lifetime of Mendeleev. He put some space. He called that element as Eka boron. Eka boron is nothing but scandium. Similarly, gallium, he could leave some space and call the element as Eka aluminium. What is meant by Eka aluminium? Gallium resembles its properties in terms of aluminium, and scandium resemble the properties with the boron. Gallium resemble the properties with the aluminium. Both are low melting. So aluminium is low melting, but gallium is still more low melting. It is a liquid metal. So germanium is called Eka silicon. Silicon is a semiconductor. Germanium is also semiconductor. So he could predict the semiconducting nature of the element, left some gap, that was observed as germanium later. So that is the merit of the periodic table. So lastly, he corrected the advantages of the Mendeleev's form, corrected the atomic weights of beryllium and indium. Be means beryllium, In means indium. So the general formula you got to remember: atomic weight is equal to equivalent weight into valency. So for example, atomic weight of sodium, so this one, atomic weight of sodium is equal to equivalent weight of sodium into valency of sodium. Valency of sodium is 1. So for sodium, atomic weight and equivalent weight are same. Calcium, valency is 2. So valency means number of atoms with which a particular atom combines. At present, you remember. You will see the details also in the first chapter. We have studied valency, equivalent weight. 4th chapter also we will study. So This valency is the number of atoms that combine with a particular atom. Sodium valency is 1 means sodium will always combine with only one atom. Oxygen valency 2 means oxygen will always combine with 2 atoms. Nitrogen valency 3 means nitrogen will always combine with 3 atoms. Carbon valency 4 means carbon will combine with 4 atoms. That is the idea. So he corrected the atomic weights as beryllium. So beryllium and indium, he proposed based on valency, corrected the atomic weights. These are the advantages of Mendeleev's periodic table. But demerits of Mendeleev periodic table: some elements with the higher atomic number were placed before elements with the lower atomic number. But why they were placed so? Because they resembled the chemical nature in that manner. The inverted pairs, they are called inverted pairs or anomalous elements. For example, argon and potassium. Argon and potassium. Argon atomic weight is 39.9. Potassium atomic weight is 39.1. So you can observe the slide and also red mark here. Violet indication and red mark inset. So argon and potassium, they are expanded in the violet background. Atomic weight is equal to 39.9 for argon. That for potassium is 39.1. Lower atomic weight element should come first. But here higher atomic element argon has come first. He has inverted the pair arrangement. That is correct. So placement is correct, but he could not explain why higher molecular weight, higher atomic weight element was placed before lower atomic weight. So that is the demerit. Another example, cobalt and nickel. Cobalt having higher atomic weight of 58.9 than nickel, whose atomic weight is 58.7. It was placed before cobalt. So this cobalt and nickel standard example question will be asked in the exam. What is the pair, inverted pair, important inverted pair is not explained by Mendeleev's periodic law, is that cobalt and nickel. But if both the elements they are rounded off, atomic weight is 59. So that on that basis 59 is same, he put in any manner. That is the idea. But if you take in the significant figures, it varies. So these are the limits. Another opposite example to the periodic law of, proposed by Mendeleev is that tellurium, Te is the tellurium, I iodine. So with this we have left in the last class. So tellurium with higher atomic weight of 127.6 precedes iodine with lower atomic weight of 126.9. Wherever except these, wherever you can check, always lower atomic weight elements will precede the higher atomic weight elements. That is the idea. So due to the inverted pairs, the place of elements in the group also changed. That is also changed. Next, last important demerit with respect to hydrogen is that hydrogen was not placed. Placement of hydrogen is not clear because hydrogen will make positive charge, hydrogen will make negative charge, hydrogen will make chargeless. All types of compounds are there possible with you have come across HCl, hydrochloric acid. It splits as H plus and Cl minus. If you take the case of water, H2O. So here it is neutral, it is not charged. Water is neutral. On the other hand, there is a compound called sodium hydrate. These compounds we will study in the next chapter, chemical bonding. Sodium means sodium will always be present as sodium plus. It will lose its electron. The last electron by sodium will be taken by hydrogen. So hydrogen will be negatively charged. So all are hydrogen. Hydrogen is positively charged in hydrochloric acid. Hydrogen is neutral in water. Hydrogen is negatively charged in sodium hydrate. So An element can take either positive charge or negative charge or neutral. For example, sodium means only positive charge. There is no sodium negative. Wrong. On the other hand, helium means always neutral. It will neither for positive nor very difficult to form its positive charge. Can be formed but very difficult. But if you take the case of halogens, halogens will form negative charge. Halides, chloride, bromide, nitrate, like that. So chloride, bromide, iodide, they form negative charge. But hydrogen forms all types of elements. Positive charge, negative charge, zero charge. So it is whether it is electropositive or electronegative or electroneutral. That placement was not clear as per the Mendeleev's periodic table. And there is a type of elements which we will study a bit later. These are called lanthanides. There is a metal called lanthanum. LANTHANUM. This is called a metal called lanthanum. The metals which behave like lanthanum, these are called lanthanides. Lanthanides are the metals behaving like or similar to lanthanum. Lanthanum symbol is capital L, small a. So these are called lanthanides. So lanthanides, where they are placed, they are not collectively placed at one place. Lanthanides are randomly distributed. Ruthenium, rhodium, palladium, osmium, iridium, platinum, iron, cobalt, nickel, all are lanthanides. So they are not properly placed. So it is not certain. Lanthanide means they have to be present as a group or as a period. Here they are present both as group as well as period. So it is not certain. So these are the limitations of the Mendeleev's periodic table. Inverted pairs, clarity in hydrogen position in lagging, uncertainty in the position of the lanthanides. These are the limited. So for to be any type of question, they will ask for the understanding purpose. What are the limitations of Mendeleev's periodic table? Inverted pairs, position of hydrogen is not clear, position of lanthanides is not certain, uncertain. So these are, let us see, already we have seen anyhow. Mendeleev's periodic table is based on atomic weight or atomic number or number of neutrons or specific heat. So good evening, Amit, Amit and Selvaraj Srija. So you can try. So Mendeleev's periodic table is based on atomic weight. Moseley's periodic table is based on atomic number. Major difference. Modern periodic law or Moseley's periodic law is based on atomic number. Mendeleev's periodic law is based on atomic weight. So atomic weight. It is Mendeleev's periodic table. Periodic law is based on the atomic weight. Already we have seen. Next is considering good. Dhanalakshmi and Dhanapa Alavar. So Condeban also right. Nice. Condeban. So this considering the chemical properties, atomic weight of the element beryllium Be was corrected based on valency, configuration, density, none of these. We have seen atomic weight is equal to equivalent weight into valency. One formula just now we have seen. In this which you have, so valency, good. So in this formula valency comes. So valency is the correct choice. He corrected the atomic weights of beryllium and also indium. Here it is asked for beryllium. The same answer for good. Nice, Condeban. And Harshit, and also Dhanashmi. Nice. So this atomic weight, considering chemical properties, atomic weight of the element beryllium as well as indium was corrected or were corrected based on valency. The element scandium is known long back, means during the lifetime of Mendeleev. Scandium was not invented during his lifetime. So scandium was similar to aluminium, means Eka aluminium. Scandium was is similar to boron, means Eka boron. Scandium is similar to silicon, means Eka silicon. It is similar to mercury, means Eka mercury. Good, on the bad. So this scandium resembles boron in its properties. So resembled, Mendeleev could leave some space for an element which resembled boron, which he found that as a good, nice, Harshit. So resembled boron, that is why it is called Eka boron, scandium. So these three they will ask. Scandium is called Eka boron, germanium Eka silicon, gallium, like that. So Eka silicon, next question. Eka silicon, silicon is also semiconductor, germanium is also semiconductor. So germanium is called Eka silicon. So Mendeleev called, germanium was not invented during the lifetime of Mendeleev. He left some space. He told that the element on that place will be a semiconductor, he has told. So it is called Eka silicon. He called it as Eka silicon. So nice, everybody. So now this cellulose, germanium, nice. So next is modern periodic table. This modern periodic table, there are different, this is also called long form of periodic table. It is based on Moseley's law or modern periodic law, all mean the same. It is based on modern periodic law. So the modern periodic law is nothing but statement that, nice, Dhanalakshmi, Harshit and Mithun Karthik Gunasegar. So long form of periodic table is called modern periodic table. It is based on Moseley's law or modern periodic law, which states that the properties of elements are periodic functions of their atomic number. That is important. Atomic number. So Moseley in 1913 he observed regularities in the how characteristic X-ray spectra of the elements. In the second chapter we have studied about the X-ray. X-ray is the port of electromagnetic radiation. So spectrum, atomic spectrum, molecular spectrum, continuous spectrum, like that we have seen. So X-rays were made to be incident on a element. Then the outcoming radiations were observed in a spectrometer. These are called spectra. So if you change the element, you can get X-ray spectra of different elements. So he conducted X-ray spectrum experiment for different elements, and then he found that it is not the atomic weight that decides the periodicity, only the atomic number. So he related, this relation is important. Atomic number Z of an element is related to the frequency of the X-ray emitted. So every element will emit the X-ray according to its capacity. So already we have seen black body is only absorber of all types of radiations and emitter of all radiation. But any element generally it will partially absorb some radiation and emit other radiations. So it will vary from element to element. So he compared the emitted X-ray. Emitted X-ray means the X-ray after traveling through the element. And its frequency he compared, and also atomic number. Here nu is the frequency of the emitted X-ray from the element. A and B are the constants. Mosley's constant. Z is the atomic number. So he found that root nu, this letter is Greek letter nu. Nu is frequency. Root nu is equal to A into Z minus B, where A and B are called Mosley's constants and Z is the atomic number. So in the y-axis, so it is like a formula. So in maths you might have studied. So this can be written as AZ minus AB. AZ minus AB. So this can be written as y is equal to mx plus c. So in the y-axis you can plot root of y. In the x-axis you can plot atomic number. So y-axis you can plot root of the frequency of the X-ray, emitted X-ray from the element. In the x-axis you can he plotted atomic number. So he observed a straight line with a slope m. That is the thing. So he inverted. So square root of X-ray frequency. So frequency can be this is the formula. So y-axis is the atomic number, x-axis is the square root of X-ray frequency. From this he could observe the relation. So here atomic number varies from element to element. Square root of X-ray frequency also varies from element to element, but it follows a smooth trend. The black dots are for different elements. Y-axis is the atomic number of the particular element. X-axis is the frequency of the X-ray emitted from the element. That is square root of the frequency. So he can draw a graph in this fashion. Initially for some elements it was straight line. Other set of elements he could observe a curve. That is why he has taken square root. So y is equal to mx means it is a straight line, but y is equal to some constant into root x. If it is there, it is a curve. So x power anything other than 1, it is a curve. Generally, so you will study in the maths analytical geometry later. If you have y is equal to ax means x power 1. X power 1 means it is a straight line. But y is equal to mx power n, where n is a fraction or other than 1. If it is other than 1, it is a curve. So equal to 1, it is a straight line. So line is a particular case of curve. That is why. So he could observe the curve. So let us not go into the maths now. So this line and curve, how they vary. So this is the second element. This way he found that the atomic number is only the fundamental property and not the atomic weight. So everything is correct according to Mendeleev. We cannot reject Mendeleev's postulate. Mendeleev has found the properties of the predicted. He has not found. He has predicted the properties of the elements which people would later discover. So that was his merit. So only the small word is not the function of atomic weight, it is a function of atomic number. So based on this, so modern periodic law states that physical and chemical properties of the elements are periodic functions of their atomic numbers. So atomic numbers means number of protons and number of electrons. So all the electrons are negatively charged. So they cannot be in the same shell. We have studied in the previous chapter about the electronic configuration. So and also, so two important properties which decide all other physical and chemical properties of elements are atomic number and electronic configuration. That is important. So electronic configuration, according to electronic configuration and also according to electronic atomic number, elements. So in this way, this is the long form of periodic table or Moseley's periodic table. Here you can see hydrogen is at the center. So previous case hydrogen was hydrogen is at center. Center means it can be positive or it can be negative and also zero. So zero is the center between positive and negative. So since it can take all types of properties, it is placed at the center. So in this arrangement, everybody please make a note. So first, hydrogen and helium is first period. Lithium to this Ne is called neon. So lithium, beryllium, boron. So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So lithium to neon, second period. Similarly, sodium to argon, third period. Sodium to argon, third period. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, third period. Next, potassium to krypton. Potassium is K. Krypton is Kr. So this is fourth period. Rubidium to xenon, fifth period. Cs is called cesium. So hereafter already we have seen, when you have elements symbol is two letters, first letter capital, second letter small. Otherwise each will, if you write capital C, capital S, carbon, sulfur, it will mean capital C, small s, cesium, a different element. So from cesium to Rn, radon, sixth period. Lastly, francium to unknown element, seventh period. So maximum 7 periods. So the number of horizontal rows of elements is 7. Here also Mendeleev is also 7 periods. Here also 7 periods. No change. But groups he has in the case of Mendeleev, he divided groups into subgroups A and B. He continuously mentioned the group 1 to 18. 1, 2, 3, 4, 5, like that, up to 18. So there is no subgroup A and B, etc. So long form of periodic table, 18 groups and 7 elements. See here, lastly, you observe there are two other grey colored. These are called lanthanides and actinides. Now everybody listen. Element with atomic number 57 is called lanthanum. Next to 57 you have 72. 58 to 71, all other metals behave like lanthanum. That is why they are called lanthanoids. Lanthanoids or lanthanides, both mean the same. Already the suffix oid in Greek means similar. Metal, metalloid. Metalloid is not a metal, it will behave like a metal. So it will behave like, which will be elements which can behave like lanthanum, they are called lanthanoids. Similarly, next is so 89 below that, 89 element with atomic number 89 is called actinium. It is called ACTINIUM, actinium. So actinium from 90 to 103, elements with atomic number from 90 to 103, they will behave like actinium. They will behave like actinium. So that is why they are called actinoids or actinides. So which can behave like lanthanum. That is why there is one asterisk like lanthanum, 2 star or 2 asterisk like. So these are the one. Next important classification. Here you listen. You can see them in detail. First two groups. The valence. So already we have seen about the configuration. Valence shell. What is meant by valence shell? Valence shell means outermost shell. Everybody note. Valence shell means outermost shell. Then penultimate shell means shell inner. This we have studied in the previous chapter. Shell inner to valence shell is called penultimate shell. Shell inner to penultimate shell is called anti-penultimate shell. So in the Aufbau principle and also in the N plus L rule, we have studied that after 4s you have 3D. 4s2, this is the, so first period, second period, third period, fourth period. So fourth period means shell number is 4, principal quantum number is 4. So this is S1. All this group, if you compare the electronic configuration of hydrogen, even you can include hydrogen here, because hydrogen atomic number is 1, electronic configuration is 1s1. Lithium atomic number is 3, so 1s2, 2s1. So hydrogen electronic configuration is 1s1, lithium electronic configuration is 2s1. Like that you can tell without writing. Sodium electronic configuration is outermost valence shell configuration is 3s1. Potassium outermost configuration is 4s1. Rubidium outermost valence shell 5s1. Cesium outermost configuration is 6s1. Francium outermost configuration is 7s1. Even if you write the electronic configuration, you can check. So first group outermost configuration ends with NS1. That is 1s1, 2s1. Second group, this is called first group. Second group elements outermost configuration is NS2. So 1s2, 2s2, like that. 1s2 is helium. It is inert gas. That is why it has come to the right. Why it is placed at the right? Beryllium is somewhat reactive, but helium is not reactive. Lithium is reactive, but lithium will form only positive charge. Hydrogen will form positive charge, negative charge, zero charge. Any type is possible. That is why it is kept at the middle. So first two groups of elements, lithium, beryllium, sodium, these are called S block elements. S block elements. Everybody listen carefully. So first two groups of elements are collectively called S block elements, because for first group of elements outermost valence shell configuration is S1. For second group of elements outermost configuration is S2. Similarly, coming to boron, P1, P2, P3, P4, P5, and neon is P6. Helium is 1s2. That just now you have seen. So p orbital in the second chapter. Anybody having doubt, you can raise. The second chapter we have studied that p orbital can accommodate maximum 6 electrons. Can accommodate maximum 6 electrons. Boron group outermost orbital, p orbital, contains only 1 electron. Carbon group, so these are called group or family. Vertical collection of elements is called group or family. So boron family outermost valence shell configuration is P1, NS2 NP1, like that. Carbon family valence shell configuration is P2. Nitrogen family valence shell configuration is P3. Oxygen family valence shell configuration is P4. Fluorine Valence shell configuration is P5 and neon valence shell configuration is P. What sir you are telling 1, 2, 3? Just these are called P block elements. These are called P block. So leftmost set of elements, these are called S block elements. First two groups are called S block elements. Rightmost elements excepting helium, because helium p orbital there is 2s no electron, 2p no electron. Excepting helium, all other are called p block elements, rightmost. So leftmost is s block elements because configuration is s1 or s2. Rightmost 6 groups of elements, these are called block. Block is the collection of group. First group and second group put together called S block. Third group to eighth group put together collection of P block. But in between, here these are the configuration of D1, D1, D2. So D4 can be replaced as D5 we have studied. D5 actual, D6, D7, D8, D9 or D10. So here D4 or D5, whatever be the case. Here also D9 or D10. Here actually D10. So in between, it is not valence shell, penultimate shell, inner to valence shell. Next to for us, you have 3D. 3D1, 3D2, 3D3, 3D4, 3D5, like that. So in between we can, so d orbital maximum capacity is 10 elements. D orbital maximum capacity is 10 elements. So the green colored, pale green colored elements, they have common configuration ns2 n-1 penultimate shell, d 1 to 10, ns2. So calcium is 20, up to calcium we have seen 4s2, scandium 4s2 3d1, like that. So good evening Vakit Gowda. So this one ns2 n-1 d 1 to 10, this is the valence shell configuration, and valence shell is ns, penultimate shell is inner shell to valence shell, that is n-1. D orbital can accommodate maximum 10 electrons. So this is D block element. Scandium to zinc, general configuration 4s2 to 4s2 3d1 to 3d10. Similarly yttrium, why is yttrium? In the second fifth period, 1, 2, 3, 4, fifth period, yttrium to cadmium, it is 5s2 4d1 to 4d10, that is also D block elements. So the D block elements, middle elements are called D block elements. You will see the other name for these elements bit later. These are called D block elements. These are also called transition elements. Already you have seen, and you will see them in detail. What is meant by transition element? Having more than one valency, one type of valence, more than one type of, for example iron chloride, there are two compounds, FeCl2 is also iron chloride, FeCl3 is also iron chloride. So FeCl2 iron valency is 2, FeCl3 iron valency is 3. So valency transfers from 2 to 3, that is why it is called transition element. So transition element which has variable valency, D block elements are called transition elements. These are generally colored. Generally we will see them in detail. So transition elements. Next is coming to, already we have seen lanthanum to hafnium, in between. So 57, 58 to 71, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have found that f orbital can accommodate maximum 14 electrons. F orbital can accommodate maximum 14 electrons. So lanthanides and actinides are called F block elements. Out their valence shell configuration is not a, so ns2 n minus 1d, it may or may not have electron. It's not, they are not bothered. But n minus 2 f 1 to 14. So n means valence shell. N means valence shell. N minus 1 means penultimate shell. N minus 1 means penultimate shell. N minus 2 means anti-penultimate shell. Already we have seen 6s, next to 6s we have 4f. Recall the electronic configuration. Then only 5d. So this is to be noted important. So 6s, next to 6s we have 4f. 4f means it has 14 electrons will go to inner. So these are called F block elements. Lanthanides and actinides are called F block elements, but they are only in the transition. All these are transition elements. They are only in the transition elements. So they resemble transition elements in some respects and are different from transition elements in other respects. That is why F block elements are called inner transition elements. F block elements are called inner transition elements. So D block elements are called transition elements. F block elements are called inner transition. What about S block and P block? These are called representative elements. S block elements and P block elements are called representative. What is meant by representative? Whenever you tell any compound, one of these S block or P block will come. You can check everybody. So everybody, first you give an example of any compound, water, ammonia, nitrogen. So it is any compound containing two or more elements. Any compound you take, one of the atoms will be either from S block or from P block. You can check, everybody can check, and also you can tell. So let me tell, common compound is water. Hydrogen is S block, oxygen is P block. If I take common salt, sodium chloride, sodium is S block, chlorine is P block. Chlorine is P block. If I tell glucose, glucose formula C6H12O6, C6H12, carbon also P block, hydrogen S block, oxygen P block. So any compound is represented by either S block elements or P block elements. That is why they are called representative elements. These elements represent most of the compounds that we segregate. So carbohydrates means carbon, hydrogen comes. Fats, vitamins, organic compounds, all organic compounds contain carbon. Carbon is the P block element. Now I will tell one element, one compound. You can check and tell whether it contains representative element or not. Calcium fluoride. Calcium fluoride. Calcium fluoride, the elements are from representative elements or not? S block and P block or not? Calcium is S block. Fluorine is P block. Calcium fluoride. So any compound, you tell either oxygen will be there or hydrogen will be there or halogen will be there. If I tell potassium dichromate, K2Cr2O7, K, S block. This may be D block. Chromium is D block, but oxygen is P block. So any compound is represented by S block element and P block element. So that is why it is called S and P block elements. So they are called representative elements. So already we have seen periodic table. Mouseley's periodic table consists of 7 periods, which are horizontal rows, and also 18 groups. So if you number from lithium to sodium, 1, 2, 3, like that. So left to right you can number it as 18 groups. First group, second group, third group, up to 18th group. 18 groups are vertical columns of elements. So older notation, first group A, second group A, in between the green colored were called B group, subgroup, third B, fourth B, fifth B, sixth B, seventh B, lastly eighth group was put as such, no subdivision. So once again, first B, second B, first A, first second A, first B, second B, so third A, like that. It was mentioned in the old Mendeleev's periodic table, but newer periodic table, this subgroup notation was replaced and now groups were numbered as 1 to 18. Later, this is important. So there is a arrangement. This you will study in organic chemistry in future later. Please make a note. IUPAC, International Union of Pure and Applied Chemistry. It prescribes names of elements and compounds for different species. So here groups are numbered from 1 to 18 according to IUPAC recommendation. IUPAC recommendation. So topmost, first group, second group, like that. 12th group, 13, 14, 18th group or 0th group, both mean the same. Please make a note. 18th group is also noble gases. 0th group is not 18 to 0. So 18th group or 0th group. Last group has two different names. Why it is called 0th group? Its valency is 0. Its valency is 0. Why it is called 18th group? Except helium and neon, all other elements, they will have 18 electrons in the outermost shell. 8 electrons or 18 electrons except helium. All other elements will have 8 electrons or 18 electrons in the shell. So that is why this is the naming. So how to remember the periodic table? With this we can limit. Anybody having doubt, you can raise. So period number we have told. Period number 1, 2, 3, 4, 5, 6, 7, up to 7 periods. So here what is to be noted is that period number is the highest principal quantum number in the element in the period. What is meant by highest principal quantum number? Let us check for sodium. Sodium atomic number 11. Sodium electronic configuration 1s2, 2s2. Will it be visible? 8. So sodium, let me take sodium. Sodium atomic number 11. You write the electronic configuration. So 11 mean atomic number 11 means there's 11 protons, 11 neutrons, and 11 neutrons maybe are more than, but 11 protons and 11 electrons will be there because atomic number is number of protons or number of electrons. 11 electrons will not be in the same shell. First shell 1s2, second shell 2s2, next 2p6, 2, 4, 10. 3s1. So 1 means one quantum number, 2 means another quantum number, 3 means all these are principal quantum number. So principal quantum numbers for sodium are 1, 2, 3. Maximum principal quantum number is 3. So that is why it is called 3s1. So third group, it comes in the third period. Sodium comes in the third period because in its electronic configuration outermost. So period number is the highest principal quantum number of the element. So francium, highest principal quantum number is 7. Cesium, highest principal quantum number is 6. Like that it goes. It has to be noted. So important points of modern periodic table. First period, we have two types of elements, hydrogen and helium. Hydrogen and helium, two elements. All other periods, remaining periods, that is 2, 3, 4, is not mentioned the seventh period. Why? Because some elements are not there. Even it is empty. So from second to sixth period, number of electrons. So second period 8 elements. Third period is also 8 elements. Let us check. So hydrogen and helium. Hydrogen and helium, 2 elements. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, 8 elements. Sodium 11, argon 18, 11 to 18, this is also 18 elements. But potassium to krypton 18 elements, 18 plus 18, 36. 18 plus 18, 36. So like that, krypton. Then you have 37 plus 36 plus 18, 54. 18 elements. Lastly, 32 elements. That is given in the book. That is given at the comparison here. So remaining period, 8 elements. 8 elements. Second period, 8 elements. Third period, 8 elements. Fourth period, 18 elements. Period means here it refers to the horizontal rows of elements, not our class period. So fifth period refers to consists of 18 elements. Sixth period consists of 32 elements. Seventh period is incomplete, and also already we have seen 14 elements of sixth and seventh period are placed below the main body of the periodic table. This you can see. So first period 2 elements, second period 8 elements, third period also 8 elements, fourth period 18 elements, fifth period also 18 elements, sixth period here length, so here it will appear 18, but lanthanum there is 14, lanthanoids there is 14. So including lanthanoids 18 plus 14, so here 51, 2, if you run up to here 18, but lanthanum plus, so 82. So or you can take 54 plus 32 is 86. 54 plus 32 is 86. Sixth period 32 elements. That is to be noted. Seventh period is incomplete. So next class we will see the IUPAC nomenclature of elements with more than atomic number more than 100. Atomic number more than 100. So anybody having doubt in today's class, you can raise. So don't take it as assume it to be dry. You have to segregate, note down the salient features. Any doubt? So trying to understand is best rather than the memorizing. If it is understood, it will automatically be in you. That is to be noted. Anybody having doubts? So the difference in the approach between the Mendeleev's periodic table and modern periodic table is that Mendeleev's periodic table is based on atomic weight. Modern periodic table is based on atomic number. So good. With this we can finish. We will see this later.